Hello everyone, my name is Zhou Wan, a PhD student from the Technical University of Montreal. Today I will present our collaborative work with Professor Supriya's group from Kalinga Institute of Industrial Technology. The title of my talk is Structure Behavior of DPPC membrane under cooling and lateral pressure. Simple liposomes serve as the fundamental building blocks for modern nanomedicine, including mRNA-carrying lipid nanoparticles. A major challenge in engineering their characters is striking a delicate balance. They must remain highly stable during blood circulation, yet readily rupture to release their coagulants at target state. To understand this, we use the DPPC as our model system. By pushing their DPPC barriers to their extreme mechanical limits, we can accurately predict the exact thermodynamic thresholds where these drug carriers will fall apart. So, last year, our team published a great study mapping out this structure pathway, but that study only looked at the one specific unit atom mode. That left us with a big question. Does this happen in every model? So, in the new study, we set out a rigorous cost scale benchmark. Our tested three totally different models: all atom charm, united atom revised, lipid burger, and coarse grained martini, just to see how reliable our simulation tools really are when predicting these extreme failures. Before diving into the results, here is a pretty fair overview of our computational setup. We utilize the GROMAX for our simulations and VMD for visualization. As detailed on this slide, we carefully tilted our MD parameters, including time steps ranging from 0.1 to 1.5 femtoseconds, and extend simulation time up to the 13 microseconds for the martini mode to explore more scenes. We also adapted specific cutoffs, barostats, and thermostats for each force field. To make sure we were comparing apples to apples, we tracked a few key metrics. Macroscopically, we compared the standard 2D area per lipid against the 3D APL, and we also looked at mean curvature and head group variance. Microscopically, we dug into the mass density profile, the nematic order parameter, and the tilt angle. Alright, let's start with the top left picture. What happens when we compress it? Visually, we can clearly see the membrane barnacles and get a highly undulated. In fact, that snapshot you see right there is taken actually at the equilibrium stage on the 15 bar at 323 Kelvin. But look at the chart data over here. The right line, our 2D APL just dropped off a cliff. Now we rescaled the 3D APL, the blue line does still decline, but it completely diverged from the 2D values. And if you look at the black line for variance, this shows up right here at the 15 bar. We can actually cross-check this with the mass density profile right at the 15 bar. You will notice the three peaks suddenly become lower and much broader. All of these metrics together briefly confirm that 15 bar is the actually critical threshold for undulation in the tram mode. If you look a bit closer at the timeline, this graph on the left plots the density of the revised LB mode at a negative 18 bar over a few microseconds. You can see this sharp jump right after 700 nanoseconds. This is a huge reminder that we really need longer simulation time to reach a true equilibrium. But what exactly it happened to the structure here is actually entering an interdigitated phase. If you look at the meeting graph on the stretching side, the negative pressures and there are sudden dramatic shift. Their angle jumps sharply, while the pneumatic order parameter shows right up. Both of those metrical clear tell us the limits are becoming highly ordered. We can see the perfectly on the right. The tilt angle distribution at negative 80 bars is extremely concentrated, right between 0 and 20 degrees. So instead of becoming chaotic under tension, the lipids are essentially standing straight up and deeply interlocking with each other to survive the extreme stretching. Now, stepping back from the detailed graphs, let's look at the actually visual trajectory side by side. As you can see in the exemplary collapse during compression, the atomistic and united atom models successfully transition into that unrelated state. But interestingly, the coarse-grained Martini mode behave quite differently. It skips the undulation phase entirely, and when pushed to 90 bars, it directly ruptures. And when we flip it around to extreme stretching, we see a similar discrepancy. While charm and the revised lipid burger models form that protective interdigitated phase before failing, the Martini model does not. It simply stretches until it directly ruptures at negative 110 bars. This gives us a massive visual clue. The coarse-grained resolution of Martini handles extreme packing very differently, missing some of the complex structural adaptations seen in higher resolution models. When we quantify this across all three modes on the left graph, the big takeaway is that they all capture the same qualitative expansion than the other lateral pressure. However, the actual quantitative critical values, the exact pressures where they fail, debate significantly depend on the resolution. Furthermore, if you look at the graph on the right showing European lipid versus temperature, we mapped the thermal expression. It is clear that the transition thresholds are highly sensitive not just to mechanical stress, but to cooling and heating, showcasing a complex coupled thermomechanical behavior. To conclude our findings today, our extensive cross-scan simulations successfully quantitative three main structural transition in DPPC membrane, planar to undulating under compression, bilayer to interdigitation under stretching, and ultimately structure rupture. Well, our models capture the core sequence of events. Their quantitative breaking points and phase behaviors differ significantly due to resolution. Recognizing this resolution detail is absolutely critical for researchers when choosing a mode to design a reliable lipid-based drug delivery system in the future. Finally, I would like to express my sincere gratitude to my wonderful collaborators at the UPN and the KIT. They acknowledge our founding institutions for supporting this work. Thank you all so much for your time and attention today.